It is recording now, no? 1 second. Right. So what is basically the significance of CFL number is this. So we have a grid. So this is a grid, 2D grid. Like you can say this is a 2D domain or grid, which has height, which has the length of delta x and so the flow is moving with velocity u. And so in current number is the thing is that the velocity in a single time step u delta t. So if your fluid is starting at left, it will it has to travel a distance of delta x to exit the right on the right. So u delta t is, so the point is the delta x should be large enough such that the fluid particle should not move from point left to right in a single time step. So this is the physical significance of the current number. So for example, if you have any grid delta x, so you have to choose your time steps such that the delta x is always larger than u dot delta t. It means that uh, in for that time step delta t, fluid particle should not move, should be in the single domain. It should not move from, it should not exit the it should not exit the domain like in the time step lesser than delta t. So you have to, so you have chosen your delta x, that is grid size, then you have to change your delta t according to the CFL number. The problem happens is, or vice versa, you if you have chosen a delta t, you have to change your grid like that. So the important thing is, if you don't like if the problem happens is, if CFL number is not like good, then the most of the simulation diverges. So CFL number is only significance for explicit schemes, and if your solution is diverging, then you have to make sure that CFL number is less than 1. So CFL number is basically reverse of this, that is u delta t by delta x is less than 1.
Just filter, can you add filter back?
Sure. So she can by default enter na.
She texted in the group. She texted me to let her in.
Actually, the important fundamental part is not recorded. If she has not joined, then
No, I think she was there. She by mistake got exited. It seems. Can you go on people and click request to join against my name?
she should join, like go to MS Teams and try joining na.
Yeah, I've given request to join. Let's see. She was just there. She just left accidentally. Left.
Vishnu, I hope you understood something about the fundamentals of these things. So once you see the PPT, na, maybe you'll understand better. Like,
After
I'll
12th
share,
standard, I'm seeing 5-4 from first time now.
Okay. All right. So you are from BARC, na?
Yeah.
Okay.
So we do completely different kind of math from our
Understood now.
bachelors. Yeah.
Yeah. So this is different, yes. But if you go through these slides like 2 or 3 times, you'll get the idea. Like,
Okay.
I'll share these things.
She joined.
She joined? I'm calling her.
I can't see her. Yes, she can. आपको तो सब समझ आ रहा होगा ना, है ना?
Doubt है मेरे को.
पूछ लो अभी. ये तो है ऑफलाइन का फायदा.
So what is advection means exactly?
Okay.
And why it has linear variation, right? Conduction, sorry. But why that is hyperbolic or parabolic, whatever.
So
the thing is that I haven't got.
So this is so first thing, this is just representation. So first,
So that advection means heat transfer.
not heat transfer, advection. So here I am trying to teach everything from the fluid perspective. So so if there is a fluid flow, so due to the property of the material, there will there is a, if this box is a fluid.
Yeah.
So this box is a fluid. So this fluid has a property of conduction.
Okay.
So so most of the time conduction, it is never linear in real life, but most of the time we assume it linear.
Conduction is transfer heat.
Heat. So without any medium. So if you have a bucket which is not in bucket, you have a fluid which is not moving.
Conduction, I understood.
Okay, so in conduction, we by default assume it is linear because most of the time it is linear. In engineering application, it may change, but most of the time it is linear. And what happens in advection? So now you have a bucket, okay, which was the fluid was constant or stationary. Fluid was not moving. Now, but you are moving that bucket. So if at the bottom of the bucket there was temperature T1, at the top T2, so due to conduction, there was a profile from bottom of the bucket to the top that was linear. But now you have started moving it. So the profile will change because the fluid at the bottom is also coming to top. There is transfer of fluid. So the fluid has energy at bottom. So fluid is also moving. So it is also due to the movement of the mass of the fluid.
में डायरेक्ट सॉलिड से जो
Solid to solid, it is transferring.
Molecules is
Exactly.
तो
Yes.
वाइब्रेशन से होते हैं
That understood about conduction.
कन्वेक्शन क्या होता है कि पहले छोटा कंडक्शन होगा, मतलब जो फर्स्ट लेयर ऑफ मॉलिक्यूल है वो कंडक्शन देगी, लेकिन उसके बाद मॉलिक्यूल ऑफ एयर आएगा। मॉलिक्यूल ऑफ एयर क्या होगा, हाई एनर्जी लेके भागेगा वो दूसरी तरफ, मतलब लोअर की तरफ भागेगा। तो ऐसे वो फ्लो होगा।
इसका सिंपल तरीका समझने का is that for example here AC is working. For example, AC is throwing energy with zero heat. So we'll only experience heat due to conduction. But abhi, if we increase the fan, you'll feel more colder. So because it is also taking a lot of heat, it is striking here, taking your heat with you. So it is basically motion of the fluid that is taking the energy.
Okay, movement transferring.
Yeah. So
conflict. So another.
yes. So the point is, if fluid is moving, then it will take some energy with it.
Like you have written, just go one more slide back. Yeah. Can you just shift that Zoom meeting?
Okay.
Somewhere, yeah.
All right. That's it.
So this is energy balance equation. I understood.
All right.
Okay, qx plus dx. If you write in x direction, negative. If you write that, this is fine. But what does that qb into delta v denotes here?
So QB is heat generation.
Okay, so heat is generated in that box, which we are writing.
Yes. So this is a fluid box in which heat, in which there is conduction happening as well as there is heat generation. So it may be like in a
No, I just want to confirm that is what it is.
It is,
generated.
yes.
So
it may be there is some reaction that is happening inside and it is generating heat, or there may be some heat sink which is extracting heat. It can be either way. On the right hand side is just how the thing changes over time due to the heat generation and heat conduction. So I want to again emphasize that this is not some flat plate. This is fluid particle. So conduction is happening in fluid particle.
just take
it is very infinitely small. Yeah. So in that fluid particle, this is stationary fluid particle. It is not moving. So in this case, we are also saying that there is a movement in the fluid particle. It is, if it is moving, then we have u. It has to move with some velocity. So for example, if I'm throwing you at a particle at you, which has temperature T, so you will get all the energy that particle has. It's simply like that.
Energy transfer.
Due to the motion of the particle, fluid particle. And how much energy the particle has is by how much energy it can store. mass into C, that is heat capacity.
Into 10.
How much energy? So some fluids have higher heat capacity. They can store higher energy. Some have very low heat capacity. So at the same temperature, they can store lesser energy.
There are momentum equation. You have used U by rho is equals to U.
Mm-hmm.
That is dynamic viscosity also.
That is dynamic viscosity. Yes.
We are talking here about, we are talking in terms of kinetic viscosity.
Yes. Yes. You can look into the details, but
Remember something of fluid mechanics. So
So it is just diffusion. You can.
diffusion is a new terminology. Viscosity, I'm more familiar
Okay,
with.
okay, okay.
So
Thermodynamics.
no,
It's not-
it's a fluid. Exactly. Thermo is like
So this is momentum diffusion. Yeah.
similar to. You can.
Okay. So that's the importance of offline. You can ask.
Greater than 1, what does it denotes?
So actually, this should be less than 1. I just made this like 5 minutes ago. So
So that is not Reynolds number, right? Delta
no.
is
So
into delta.
so actually,
Because
this the current number is this. Let me show. This should be the current number basically. Actually, we all have seen that current number is less than 1.
Hmm.
So it is like this. So CFL number should be less than 1. So this is a definition of CFL number.
this is current.
In one time step, the fluid particle should not move from entire domain. So it should be somewhere between.
It should be lesser than 1 for
Ah.
stable.
It means if the fluid particle is
Greater-
starting at left, it is somewhere inside the domain, not out of the domain. In single time step. So this is basic physics of CFL number. Similarly, it is for
So right now we are talking only about a laminar flow, right? Not we are not
Yeah,
talking
so-
about turbulent flow.
mhm.
So laminar flow and turbulent flow is bifurcated and you have to put charge in. Okay.
Okay, yeah.
By
Mhm.
the Reynolds number, right?
Mhm.
We generally define by Reynolds number whether flow is laminar or
Turbulent, yes,
So
yes.
what is that Reynolds number?
So
Where
it
we-
Reynolds number is just
I know what is Reynolds number,
Okay.
but I want to know the date. Like if I'm calculating Reynolds number, I should know whether my flow is turbulent or my flow is laminar. So what is the number exactly?
so number changes for different problems.
Exactly.
So
For soil, it is different. For fluid, it
Yes,
is
yes,
different.
yes. So actually there is no specific criteria for these things. So people had done experiment and they have found that after this point, there is increase in the chaoticness in the fluid. There is so in for example in my case in which I have studied flow over a cylinder and VIV of a cylinder. 1 second. Yeah. So turbulence is always there. So even if your flow is very laminar, turbulence is there, but it is so negligible, the effect is almost negligible. So as you increase velocity, so chaoticness will start to increase. For example, if you see a tap water, the if the fluid is less, it is kind of laminar, and if you open it more, it will start to see. So most of the time, the Reynolds number is always decided on experiments.
Okay, there is no such point, defined point for it.
There is no defined point. Even if you are doing any simulation of the fluid, you should always use turbulence models. But turbulence models it takes very much like computational power is very much high. So if you talk about Reynolds averaging Navier-Stokes equations, they have so here we have in fluid flow we have to solve these three equation continuity x and y, and if you have if you talk about Reynolds averaging Navier-Stokes equation for turbulence, in some models it has one equation extra, two equation. In some models it also has six equations extra. So it means you have to solve six extra equations. So it is computationally very expensive. So it is always better to avoid turbulence model wherever there is possible. So laminar flow is just an assumption, like
Yeah, because laminar doesn't
Yeah.
exist in practical. It exists,
It exists, but there is always 10 raised to power minus
Yeah.
5% of turbulence in it. There will always be turbulence, but can we ignore it or not? That is the main question. Okay, so next. So, so we have seen this. All right, boundary layer. Now, what when I show you the fully developed flow in a channel, this is what I meant. So you have a uniform velocity flow coming from the left. What it will do is it will make a boundary layer so we have a channel, we have a top and bottom plate. There is uniform flow coming from the left, and as soon as I strike both the plate and top and bottom, it will form a boundary layer, and it will start to form a boundary layer. So on the left you can see that the boundary layer is forming, and on the right you can see the boundary layer is fully developed. So when we say we have a fully developed flow in a channel, it means now the boundary layer has fully developed. It is not changing in x direction. So developing flow means del u by del x and del u by del t both are not equal to 0. The flow is still in the development stage, that is, it is changing with time and x direction. But after a point, the boundary layer is almost not changing. This happens. So that is when we call the flow is fully developed, and we say that del u by del x equal to 0 and del u by del t equal to 0. So the point is, on the fully developed flow, we have a parabolic profile. So between the blue lines and the black lines, you have a parabolic profile. And in the between the blue line in the center region, the bulk region, the velocity is uniform. And again, there is so this is not basically uniform, there is only parabolic profile. So this is misinterpretation. So this leads to a parabolic profile in a channel. So if the length of the height of the channel is very large and we have turbulent flow, then we can have bulk flow phenomena. So this is what meant by fully developed flow basically. Yes, yes. With time and in x direction as well. Yes. As the same thing. Yeah, yeah.
Talk about uh,
Yes, yes. So that's what he showed yesterday, now in the simulation. So now the one of the main question that is there yesterday was what is convergence and what are the various things. So for that, the previous PPT that I have made is very much, it will be very large, so I'll not go into too much details. So I'll just explain the simple algorithm. Okay. So do you guys want to understand the basic of what is discretization? I will go ahead. Otherwise, I'll just. So do you want to know the basic of discretization? As now I have explained you the. Now as I've explained you the equation, what are the equation momentum and uh, temperature equation. Now I can show you little bit about how the discretization happens and why do we need it. Should I go ahead with explaining that?
What is discretization?
Yes. So should I explain that? Like, okay. So I'll try, and if you guys. 10 minute, 10 minute. Discretization and वो convergence criteria. So I'll try. Okay.
I mean, basically what it is, you can just tell us and like how we can apply it, and then
Okay. So for BR
if you feel
guys,
it's too complex.
especially for you, I'll explain some few things. Okay. So the thing is, so this is the equation, momentum equation that we have seen. Okay. So, but in this we can apply scale analysis, or we can assume many things, and this the momentum equation that you see at the top, this is U is basically momentum in x direction, and P is pressure, R is the radius. This is flow inside a circular channel. So in this case, in a fully developed flow, as I told you, we can simplify the equation, and we can simplify the equation as 2. Considering delta P or delta X is constant, in this case, we have analytical solution possible for this fluid flow. For fully developed Fourier channel, we have analytical solution for 2D heat conduction equation. This is 2D heat conduction, which in which on the left we have transient term, on the right we have conduction term. All right. In these cases, we also have analytical solution possible in some of the cases, and these are the possible ways. All right. So now also in 1D transient heat conduction, analytical solution is possible. So there are fluid flow cases or scenarios in which analytical solution are possible, and we don't need CFD or numerical method for those. But if we have a more complex equation, for example, here temperature, I am also adding advection, that is Ux del T by del X, Uy del T by del Y, the second and third terms. I am also adding advection. So this becomes a complete variable transport equation for temperature. So this equation also becomes non-linear. So these equations, we don't have analytical solutions. And the some boundary condition most of the time is very complex. So for these cases of like fluid mechanics, we need numerical methods. So important, this is very important, numerical method. First, for example, you have this whole domain, this complete domain on the right. So what we do, the first thing is we divide the domains in many parts. Okay, so first is domain discretization. It's like, so you have a rectangular box, you cut those boxes in many parts as you want. So from one box, you are having 100 boxes. So that is called dividing your domain in very large number of discrete control volumes or grid cells, control volumes or grid cells. That is the first step of CFD that you do in meshing. All right, so this part of domain discretization is done in meshing. Then variable approximation is not of that much use. So then we have equation discretization. And then we apply the boundary condition. Now, what is equation discretization? So the key point here is when we do domain discretization, the PDE, the single PDE, for example, for heat transfer, for temperature equation, the single PDE is converted to number of linear algebraic equations that are like Ax equal to B matrix form. And those equations are same as number of the grid points that you have. So for example, if you are dividing in 100 grid points, you'll have 100 linear algebraic equations. Okay. So now we'll move to the what is equation discretization. So this is Taylor series. The fundamental of discretization comes from Taylor series. It says Taylor series provides a method to approximate derivatives by expanding the function around a point. So it is nothing like, for example, there is single domain. There is 1D domain. There is one point at I and another point at I plus 1. So what we say is this one. This will be better. So what discretization is for 1D to understand. So there is a rod, okay, in which heat is flowing, and we divide that rod. First is domain discretization. So we divide that rod in 100 parts, let's say. The first part is I, then I plus 1, then I plus 2, and then I minus 1, and then I minus 2. So now what we have is, first we have del T by del X in most of the equation. Now we don't have analytical solution for it. So we just approximate it. How we approximate del T by del X? At I, we approximate it, we say Ti, the value of the temperature at Ti plus 1 minus the value of temperature at Ti divided by delta X. That is linear gradient. So we consider in forward difference, we consider linear gradient. So basically, what we are doing in discretization is for any derivative, first order, second order derivative, we are trying to approximate is using the discrete points. Okay. So this is what we are doing in the second order, in del square T over del X square, that is second order derivative. We are doing the same things. So basically we are approximating the derivatives. Then what we will do, so for example, this is 2D steady state heat conduction equation. Okay. In two direction, X and Y direction. So what we do, we have two derivatives here, but what we do is we approximate this derivative using the discrete points. And this is how we, so we have points in, so we divide the domains, and from the neighboring domains, we approximate the derivative at particular point. And from that, we get the discretized equation, which is at the bottom. And ANSYS is also solving. So yesterday I showed you the heat conduction equation in ANSYS. How to solve heat conduction in ANSYS. ANSYS is also solving this equation 23 only. He is not doing anything fancy. He is only solving this 23 equation.
Okay.
So
Can you just go
yes,
back to that 1D? Yeah. So here finally, once we do the discretization like through the I minus 2, I minus 1. So what happens after that? So we do the different points, we do the different dt by dx, and then what is happening at the end?
so first, so we have divided the domain and we have to find temperature at I. What
Yeah.
is the temperature at point I?
Yeah.
So before finding the temperature at I, we have to find the what is del T by del X at I, right?
Right.
Because we
Yeah.
have to put that in equation. So
Right.
what we do is we simply say that temperature gradient del T by del X at I is nothing but Ti plus 1 minus Ti divided by the delta X, that is the distance between the two. That is
Mm.
simple discrete form of gradient.
Mm.
So we have now like approximated the gradient. All right. That's what we need. We need approximated gradient at every
Right.
point in the domain.
Mm-hmm. Okay.
So so in this case, we have heat equation. What we are doing is we are approximating these second order derivative del square T over del X square and del square T over del Y square at every point in the domain. And then we are solving by iterating it. So for example, the equation at 23 that you see here will be solved by iteration. So when I say iteration means, let me show you. After iteration, you will easily understand what the convergence criteria is. If you understand what iteration is, you will understand the convergence criteria. There is nothing fancy about it. So you understood that there is equation 23, right?
Yeah.
So this is 2D steady state country with heat generation. Nothing extra about it. So the equation that you see, this equation. This equation is that you see is
Mm-hmm.
obtained by
Okay. Okay.
approximating the gradients, right? What we do
Mm-hmm.
is we took the Tij, this term to the left and throw every other time to the right.
Okay. Mm-hmm.
Okay, but like these are all are approximated values. So
Right.
what we usually have to do is to get good result or get accurate result, we have to solve it again and again and again and again until we get a good solution. Like we get actual physical result. So
Oh, you
yeah,
compare it till you get the experimental result also.
or
Okay.
experimental or some result that you make sense of.
Right. Right. Okay. Okay.
So you have to again do it again iteratively. So that I'll show you this MATLAB code. So this is the code for steady state 2D heat conduction with heat generation. So I'll note, so here we have domain with length 1 and 1. We are dividing it in 20 equal parts in X and Y direction both. All right. So, and here we are applying boundary conditions of temperature at left, right, top and bottom boundary. And here where we are doing the iterative part. So for example, we are saying while the error means the error between two successive iteration. We are saying while the error is greater than tolerance. So for example, you have set a tolerance of 10 raised to the power minus 6. So if the error between two successive iteration is not less than tolerance, till then it will keep on doing this. So this is the iterative part, one iteration. So till we get the convergence which is tolerance, it will keep on repeating this until this error between the two successive iteration is less than tolerance or convergence. I hope this is clear.
Yeah. That's why yesterday, like you said that within 26, we had actually been within the we got the
Yes,
result
yes,
within the tolerance. Yeah.
yes.
Okay.
So I'll run this and it will show you that converge in 771 iteration. So from where it is showing, I have shown here iter parameter. So it is storing how much while loop it is going. So as soon as the error becomes greater than tolerance, it exits. Converge in 771 seconds. and this is the temperature profile that you get, because heat generation is very high. It is like this. So I hope the tolerance is, you understood the tolerance. So in simple algorithm, so I think all these things are clear now. Yes. Okay. So now there are two things for steady state. Steady means you don't have concept of time. For steady simulation, we have the algorithm which is called simple. It is called semi implicit pressure linked equation. Okay. And we have another algorithm which is called PISO. So for PISO is used for transient simulation, and simple is used for steady simulation. If you want to go me to explain this, I will go. Otherwise, another Abhishek will start. So I'll just go. I simply explain things. So first is initialization. Then we solve the momentum equation. U V. Then we solve the pressure, and then we see if the velocity is correct or not that we have got, and then we try to find the convergence. Convergence basically continuity or UVP, are they converged or not? Are they under tolerance level or not? If they are converged, simulation will stop. If they are not converged, it will again to momentum equation and then repeat this, and it will keep going in circles till we get convergence. Vishnu, is that clear?
Yeah, got it.
Okay. In PISO, what we happen is PISO we want solution at each time. It is a transient simulation. For example, if you have time from 0 to 100, you want to know the exact flow field at each and every time. So in this we have a little bit difference. First we have initial condition at t equal to 0, then we predict momentum or UVP, that is velocity in x and y direction at time t. Then we solve pressure correction, then we do some kind of velocity correction, and we look for the continuity and convergence. Okay, so now if this continuity or convergence is achieved, okay, then it will go to the, if it is not achieved, it will go to the this part, and it will again solve this 1 2 or 3 steps. If it is continuity convergence is achieved or overall convergence is achieved, then yes, then it will go to the next time step. So for example, if it is at 0 t equal to 0.1 right now, if not achieved, it will again solve this loop. If it is achieved, it will move to the next time step, and when all the time steps are complete, the simulation will stop. So in transient simulation, the simulation will only stop when the time steps are complete. Any question in this? Otherwise, then on the Abhishek will come and okay, fine. Abhishek's up.
Hello. 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 Shall I start? Okay.
उसका है ना ठीक।
So, hello. Yes, you are audible. Okay, fine. Then I'll start. Hello. So, can I explain again how the become model? Next, I'll tell you how the actually done the You can open your workbench, open the design model. Open geometry and targets. Take a sketch and select the plane. Let's say X open. XY plane and click on look at this. So that will be converted into a 2D. Now click on XY plane and create a new sketch. Okay. Start sketching. Okay. Can you hear me?
Your voice is kind of muffled. Very distant. Is it the same for everyone? I'm not sure if it's my issue. Yeah, it's the same for me also.
It audible?
Now it's. Can you say something again?
Is this audible now?
No, it went back. Again, your sound is muffled.
Hello. Guys, we are moving to the Google Meet. Please share the link in like 1 minute.